Last week in new material we're going to look at is on vectors. We're going to split it into 4 lessons, 3 sections. First section we're going to do over 2 days, 5-4 today and tomorrow, 5-5 on Wednesday, and then 5-6. It's kind of a review. Right? Even though it's a new section, it's doing everything that we're going to do again Monday through Wednesday, except Monday through Wednesday we focus on 2-dimensional. Wednesday it extends everything to 3-dimensional. So it's like all the same formulas again, just doing it in 3D. So it'll be a good kind of review. All right. Does anybody know what a vector is, or what you use it for? Oh, Eric, you mentioned you were in physics. Have you studied vectors?
It was last year that I took physics.
Oh, last year?
Yeah. I don't really remember it.
You're not sure. So a vector. With nines. It represents 2 things at the same time. It's used to represent anything that has a magnitude and a direction. All right. What do I mean by magnitudes? Anyone know what I mean? Like, what's a magnitude? Yeah.
Making it larger.
All right. So making something larger. Not necessarily making something larger. Like when you talk about like an earthquake, they describe it using a magnitude. And when they describe it, how do they usually, like if you hear about how dangerous or how powerful the earthquake was? They what? What do they tell you to describe it? How do you describe the magnitude of an earthquake? A number, right? A number. So yeah, they give you like a 2.5 or whatever it is. So an earthquake is described by a magnitude, but earthquakes don't really have direction. They just kind of start at a central point and just propagate out in every direction. But can anybody think of something that has a number that you can describe it as, and that number goes in a certain direction?
Line.
Okay, how about something like real life, like a real situation where you'd have to describe something to someone. You'd have to say, here's the number to describe it, here's the direction to describe it. Something in real life. Yep.
Giving directions like in a car.
Okay, how about something specific about a car? Like if the car is driving.
What you saying, say Route 95 east, something like that?
All right, so a direction, if you're trying to tell someone where to go, it has a direction. And there's a number. What would be the number?
So like Route 95 east, something like that.
Okay, so like a certain. So Route 95 east, that's all a direction, right?
There's a number.
Well, it's a name, right? So 95, it's really just the name of a road you're taking. But if you say.
So like the address of a house is the point of the house, right? That would be the number.
All right, but a house doesn't really have a direction to it. It does have a number. Like if you wanted to say like that house, you could say that's house 24.
What about like turn right in 200 feet?
Turn right in 200 feet. Okay, so you could kind of describe that as a vector. How about something else related to a car? What else as the car as you're driving? What if you wanted to describe like a car moving? How would you have to describe it? You'd have to say 2 things about it.
What would you do, like degrees of like a turn?
Yes.
Okay, so degrees of a turn. Let me think.
Taking 90 degrees.
So that would be like a direction. What else though can you describe about a car? Besides like the degree it's turning, or like if it's moving east or west.
Speed.
The speed. That's the other thing. So one thing we use vectors for is to describe anything that has a velocity to it, right? Like a car. You could say the car is traveling east on this road at 20 miles an hour, or it's traveling east on the road at 30 miles an hour. So that's a vector because it's describing the speed and the direction. Another thing is force, right? If you're pushing on an object, right? Let's say I'm pushing on this table. I could push on this table down with 100 pounds of force, or I could pull up on the table with 100 pounds of force. Same amount of force, like the number part, but the direction that I'm pushing is different. Right? So when you describe a force, 2 things you have to say. how hard are you pushing? What direction are you pushing? So an example of velocity we said was cars. Another one is like airplanes. So this is a map of air traffic in our area at the moment, well, surrounding area. And each one of these planes has a magnitude and it has a direction. Right? If we click on one, let's just see, you might be able to see some information about its magnitude and direction. Well, there's its magnitude, okay, 409 miles an hour. And the direction, well, that's indicated by this route, all right? So the plane is taking different turns, but it describes it, I guess, as a compass heading. So north is usually, you know, I'm trying to think, when you have a compass, I think north is usually 0 degrees, east is 90, south is 180, and west is 270. So this plane is mostly flying east, right? 70 degrees, 80 degrees, 90 degrees, 100 degrees. That's mostly east, northeast, southeast, but it's pretty much traveling east. All right, so there's the direction, and then back here was the magnitude. Where was the magnitude? Well, actually, that makes sense that it's traveling east because it left Detroit and it's going to Boston. So that's definitely east. Oh, the magnitude was when I clicked on it down here. Right. So speed. Oh, that's a different one, but whatever. 354 miles an hour.
That's a long flight.
When is it?
Yeah, it's a long flight. So you can see that these are some of the planes, probably not all the planes that are in the area right now.
Probably just Philly.
But the idea is that each one of these planes has a magnitude and direction, so you can represent it as a vector. Now, it's someone's job to coordinate all this. Question?
What?
Question?
No.
Yeah, you asked that actually.
Yeah, so at all the times plane has flown, do you think at any time the plane has ever dipped head on? Or like side or anywhere?
I mean, I know on the runways they've had collisions.
Or go in the air, do you think?
I don't know if in the air.
It's probably happened like once.
That's what I'm
maybe.
thinking.
think so?
Everything's had to happen at least once.
But that's the job of an air traffic controller. So any of the
Yeah,
traffic
they're really good with that type of
Yeah,
stuff.
what about like back in the day though when they didn't have
when they didn't have it, I don't know.
It was on
I'm not
the
sure.
plane has ever hit it?
Yeah, I don't know.
That's what I was which is at least one person.
But each airport has a tower, and they coordinate the traffic, and a computer can kind of look at all these planes as vectors and make sure that, you know, within that area that the planes are, you know, spaced far enough apart that things should be okay.
These things are
Now,
overlapping each other.
it looks like, yeah, but that's different altitudes probably. So one of them might be at like 20,000 feet, one of them might, you know, be at 2,000 feet. So that's a little more complicated because this is actually 3D. And if you zoom out, let's see
So there's
here.
stacks of planes right there at different ends.
Thought I could zoom out, maybe not. But if I could zoom out, you could see tons. You'd be able to see tons of traffic. Let me just refresh it, maybe see if that will let me zoom out. Oh yeah.
Yeah, you can.
I didn't see the
arrow.
arrow.
Oh yeah.
So you can see definitely when you get near certain airports, down in New York, over by Boston, and the more you zoom out, eventually, I don't know why I think he keeps disappearing, but you'd see tons, you know, tons of traffic. Right. So that's one example where vectors are pretty important. Okay.
I don't think there's that many planes in the U.S.
You don't?
I don't believe that.
Oh.
I don't believe there's probably that many planes flying right now.
I'm not sure what to tell you.
Yeah, I'm kind of the same on that one.
I mean, if you look up how many, if you look up how many planes or how many flights on a daily basis, I don't know, you could look it up and see. But, I mean, yeah, how can you verify it for sure? I'm not, I mean, you can click on one and see,
You know, right now, dude, the whole coast has planes.
Yeah, that's what I'm saying.
They look up, there's no skies, bro. It's only planes. Just at different angles.
So this is just showing all the different. I don't know what this is showing. This is some are green, some are blue.
No, this is you clicked on a
an airport?
not a.
So I mean, there's information for each flight. You know, identifying it and stuff. But maybe you think all that's fake.
Have you ever been to an airport before?
What?
Have you ever been to an airport before?
Yeah, and there certainly isn't hundreds of planes at each airport.
There's a solid amount though. But I feel like if every single airport was going at once, there may be.
There's planes taking off like every 2 minutes at airports.
Yeah.
Oh yeah. When you're at like Logan or something, I've kayaked out in the Boston Harbor, and there's a plane going over me every 60 seconds. They're not that. I mean, you don't really see them super close together because they keep them. I don't know what the rule is, but they probably keep them like 3, 4, 5 miles apart.
That'd be a cool job.
But yeah, they go over every 60 seconds. There's another plane.
Like
So.
if you like 7 buildings.
And they come from different directions too, depending on like, you know, if you're taking off or you're landing. They use different runways, but. So when we represent vectors, what we're going to do is, at first, we're going to represent it as an arrow. Okay, so an arrow is a pretty natural way to represent a vector because an arrow automatically has a direction to it. Now, how do you think I would use an arrow to represent magnitude? So the way the arrow points, there's your direction, but what about the arrow could be the magnitude? If I had 2 cars going in the same direction and I wanted to represent one's going faster, how could I draw the arrow to represent that that car is going faster? The length, yeah. So the length of the arrow is going to represent the magnitude, which can start to get a little time consuming because if we're drawing things to scale and you have to draw that arrow a certain length, then you might have to measure it. Or the other thing that runs into is if you have a really, really big magnitude, you're going to run out of room on your graph paper to draw arrows, unless you get into changing the scale. All right, but that's the idea. Length of the arrow represents your magnitude. The direction it points, well, there's your direction. Any questions on that? All right, so if we have 2 points, that's what you usually want to describe when you have an arrow, a start point and an ending point. Right? So let's say that we have a vector that starts at P and ends at Q. In geometry, that's how you would name it. That's the notation for array from geometry. You put an arrow on top. The arrow on top of the 2 letters has nothing to do with the direction. The arrow on top tells you that this is a ray. Right? If you put just a straight line on top, that would tell you it's a line segment. Double-ended arrow tells you it's a line. So that arrow on top is just there to tell you that what's below is a ray, not necessarily that it points to the right. And the order you put the letters in is important. You don't just put them in alphabetical order. You put the first letter is where you start, the second letter is where you stop. So from P towards Q. Since P is where you're starting, okay, we call that the initial point. Q is where you're ending. We call that the terminal point. Now, that notation is fine. That's what they use in geometry a lot. But we have another way that we can write vectors that's shorter than that. So sometimes what we do to make it shorter is we just give a vector a single letter. That's it. We just say that vector is vector x. But what else in math do we use letters for? Letters represent what? Unknowns or variables. So that's a problem. How would we know if that letter is a variable or is it a vector? Well, what we do is we make it, you can do 2 things. One, you can either make it bold. So if you write down a bold letter, Okay, our book uses that to mean a vector. Or you can write a letter and just put an arrow on top of it. Right, so if we drew a vector on paper and we wanted to call that vector M, you could either make it an M that's bold or put an M with an arrow on the top. If you write just a single letter that's not bold, no arrow, that's a variable. So any question on the short way we can write a vector? We have two choices.
It's not gonna be. Is it gonna be in every single time?
It can be any letter that wouldn't be confused with a number. Like letter O would probably be a bad letter, but could be any other letter. Just like in math, if you were solving for something, like you could use the letter X in your equation, or you could use Y. You can use any letter, just as long as it's not confused because it looks like a number. So L might be a bad choice for a vector, unless you make it cursive. All right, so what we're going to look at is 3 different operations with vectors, how you add them, subtract them, and multiply them. Multiplying we're not really going to get to until Wednesday. But we'll look at adding and subtracting today. All right, so let's think about what would happen. Let's think about it in terms of a force. Okay? If I'm pushing down on the table with 100 pounds of force, and then somebody else comes along and pushes down on the table with 100 pounds of force, what's going to happen now? Assuming the table doesn't collapse. The table just stays right where it is. So I push down with 100 pounds of force, somebody else comes and pushes down with 100 pounds of force. Describe what the table is feeling now. Yeah.
200 pounds of force.
Can you be a little more specific?
It's getting pushed down by 200 pounds of force.
Pushing down with 200 pounds of force. So if I push on it with a force, which is a vector, and somebody else comes and pushes on it with a force, which is a vector, what ends up happening is now we have a new vector. Possibly a new direction, and possibly a new amount of force. Now, if 2 people are pushing down on the table, you're working together. So there's no new direction. Let's say that I push left on the table with 100 pounds of force, and somebody else pushes right on the table with 100 pounds of force. Now we're fighting each other. All right? So what would happen there is, essentially, the table doesn't move. Right? It doesn't move because you're pushing in the exact opposite directions with the exact same amount of force. All right? So the idea is when you add 2 vectors together, the answer is a new vector. Another example would be, let's say an airplane is flying. And let's say that the pilot looks at his instruments, and there's no wind out, and it says he's flying at 200 miles an hour. Well, if all of a sudden we had a wind blowing the plane from behind, a tailwind, what would that do to the speed of the plane? It would move it faster, all right? So we've got the plane moving, and the wind pushing it along moves it along faster. So any questions on that idea? Plane is moving at 200 miles an hour. Wind all of a sudden blows the plane at 20 miles an hour from the tail. It's going to push the plane faster. All right. So that's another example of 2 forces working together. The opposite of that would be a headwind. The plane's flying into a wind. It's going to slow the plane down. All right. So we're going to talk more about that example with the plane. And there's an important difference when a plane's flying between the airspeed and the ground speed. All right. So we need to distinguish that when we go through the word problem, but that'll probably be tomorrow. All right, so let's say we want to add 2 vectors together. The way I'm going to show you how to do it first is visually. Okay, how do you draw it out, and what would it look like when you add them together? Let me show you what you do first, and then I'll write out what I'm doing. Because it's a lot easier for me to show you the steps. It's a little longer to describe it. But I think if you see it, you'll see it's very simple. Okay. Let's say that that represents vector v. And this represents vector w. If I want to add those together, what I want to do is connect them like that. I put the end of one at the beginning of the other. Okay? So that's how you connect them. And then the final answer is when you connect the beginning to the end. So if I were to take the vector in black and the vector in red and combine them into a single arrow, that's what it would look like, combined together. Which kind of makes sense, because the one in black goes up and to the right, the one in the red goes to the right and just down a little, not much. The combined effect of these two together would be this right here. So let me write out what I just did. So you've got to position the vectors so that the terminal point of one of them is right on top of the initial point of the other one. That's how you line them up. So you take your first vector, and then you stack your second vector right onto the end of it. Now, that's not the answer. That's just how we're going to set up to get our answer. Now that we've done that, you're going to connect the initial point of your first vector, which is right there, to the terminal point of your second vector. It's almost like you're connecting the diagonal. It's basically what you're doing. Just like that. Sometimes it gets kind of hard to see with all the arrows, especially if your lines are thick. I think it's easier to see if I move it off a little bit like that. Okay, but the final answer is when you connect where you started to where you finished. And now you can do this for as many vectors as you have. So you have one like that. So you have one like that. One like that. And then another one like that. And you wanted to know what would be the effect if all these vectors were combined into one. Okay? Think of these as different directions, like pushing or pulling on something. Well, if you combine them all together, it would look like this. Okay, the ultimate effect of all those vectors acting together would basically be this. It would be basically just pushing down and to the right. Right? Now, when you connect them, you always connect them so the arrows follow a path. All right? So it's like you're following a path of arrows. If you connect and something looks like this, you've done something wrong. All right? The arrows should follow a path from beginning to end, kind of like a one-way street. Right? Shouldn't have something like that. That's all messed up. This one should be like over here. Follow the path.
So you can do arrows in any order, right?
Yeah, we're going to mention that in a minute, but
Will always be the same.
it'll always be the same.
Like the same.
Yeah.
Vector at the end, no matter what order you put them in.
So let's say I put this one, and then this one, and then I do this one, and then I do that one. If I connect where I started to where I finished, it still comes out exactly the same. Yep. Yep. It's kind of like adding 2 plus 3 plus 4 and then doing 4 plus 3 plus 2. You can change the order you add them in and it doesn't make a difference. But I'm going to mention that more in a second. Okay, so let's just add these two up. And even though I just said the order doesn't matter, let's just do it v plus w. Right, so we take v. And I don't know, it's kind of hard to write in your notes, but if you just label them v, w, and then v plus w would be just like this. Now you can't see the arrowhead. It's kind of hard there because it's all, my lines are like kind of thick. So I'm just going to move it off it and label that. That's the answer. It's a picture. And it is important that it's pointing that way. Okay? So you've got a force pushing down and to the right, another one right. So the final answer is even more down and to the right. Okay, any question on that? Now, besides the arrow on top, how else could I have written these letters? So you know that they're vectors?
Bold.
Bold, right? I could have bolded them, but if you're writing it in your notes, it kind of takes a while to, make something bold. It's quicker, I think, to just go like that. But if you want to make the time and make the letters bold, that's fine too. All right. Let's look at this one. Before I do it, what do you think's going to what's going to happen here?
It's gonna be like this.
They cancel out. How come they cancel out?
Is it right over each other?
2 reasons. How would you describe how these vectors compare to each other?
They're just opposite.
Opposite what?
Directions.
Yep. Opposite directions.
Same length.
Same length, same magnitude. So opposite direction, same magnitude. So we're going to connect. We're going to connect where V ends and where W starts. I'm going to line up those dots in red. That's how I add them. And then when I'm done, I'm going to connect where I start to where I finish. But when I move the red dots so they're on top of each other, the green dots end up exactly on top of each other, and they cancel out. So what do you think we get here? How do you think I would write the answer? It's kind of hard to write it visually because there's nothing to draw.
A dot.
There's not even a dot. It's like it totally cancels out. So there's nothing, it's a good guess, but there's nothing to even draw. So we got to write the answers in a different way. How would you write it in addition or subtraction if everything canceled out?
0.
0. But if you write 0 like this, what did I just draw there? That's
A number.
That's a number.
With an arrow over it.
Yes, because we just said when you add 2 vectors, the answer is a vector. You don't get a number. So there's 2 ways you can write your answer. You can either do this, and you're telling me that it's 0, the vector, or you can write it like that. So this is called the 0 vector. It's it's a special vector. It's the only vector that doesn't have a direction. Okay? It's a special case. Every other vector, it has a direction and it has a magnitude. This one doesn't. So it's a special case. That's how you write the answer. All right, so we already mentioned this earlier, but I'll do it again real quick. Vector addition is commutative and associative. Commutative means you can do something like this. I'm not going to do it with 4 vectors because that takes a while, but I'll do it with 2. I'll draw it. If you do V plus W and then W plus V, you get exactly the same thing. Now, you might be thinking, well, yeah, isn't addition always commutative? You can't just assume that it's commutative. It's commutative with numbers, yes. But now we're doing vectors. We can't assume that everything we know with numbers automatically works with vectors. Some of it does, some of it doesn't. Right, so this is something that does. So let's do V plus W. So I'm going to take V. And this is really something you should just watch. Put W on the end. Now if I used a ruler and actually measured and did it nice, it might come out a little better, but it's probably close enough. So that's V plus W. I'm going to put it under the left part. Now let's do W plus V. So there's W. Now I'm putting V on the end of it. Let's draw that. And now if you compare the two, and it's not perfect, but they're pretty much the same thing. All right? So there's W plus V. Any questions on that idea? So vector addition is commutative, and it's associative. Associative doesn't have to do with the order. ABC, ABC. Same order on each side. Associative just has to do with what do you do first. Okay? what takes precedence over what? Are you going to add A and B together first? Or do you want to do B and C? With vectors, doesn't matter. Just like with numbers. All right, so let me do what's on the left. Let me do A plus B, and then I'll add C onto the end of it. Okay, so just try to remember which one is which. So C is the one that points left, B points down, and A points up and to the right. All right. So there's A and B. Put that there, and I'm just going to put that back. So that's A plus B. Now I'm going to add C onto the end of it. Okay, so the final answer, connect where you start to where you stop. Looks kind of like that. And I don't need this anymore. Question on A plus B plus C. All right, now let's do A plus B plus C, but let's do B and C first. So here's B, and here's C. All right, so let's do that. So we're done with that, we're done with that. There's B plus C. And now I'm going to do A, and then put that on the end of it. So here's A plus what I just did. Okay, well, let's do that one. Connect it. And again, it's not perfect, but it's pretty close. All right. So again, order doesn't matter. Associative property works with vectors. All right. We just kind of did this visually, but technically there's something wrong there, the way I wrote that. What do I need to fix? What?
Line on top of the 0.
Yeah, it's something with the 0, because to me that 0 doesn't look bold. It doesn't look, there's no arrow. The V's look bold to me. I can kind of tell those are a little bolder. But either make that bold, like the V's, or putting the arrow on top is probably a better way. It's less confusing for people. If you're doing it like typed out, bold is pretty clear. But handwriting bold might not be as clear. So we already said this earlier, but the difference between V and negative V isn't the length. Length is exactly the same. It's the direction that they point. So they have the same magnitude, but they point in the opposite direction. Now, look what we just did here. Something plus negative something. What are you really doing there? If you take something and you add the negative of something, what operation is that?
Subtraction.
That's really subtraction. So keeping this idea in mind, when you want to subtract two vectors, which is what we're going to do next, all you have to do is think about, oh, okay, subtraction is the same thing as adding a negative. And a negative, all it does is change the direction. Okay, so keep that in mind, and now we're gonna look at subtraction. So if I had two vectors like v minus w, and I wanted to subtract them, but we don't know subtraction yet. We know addition. So think of it this way. Think of it as addition, but think of it as adding the opposite of w. Can someone remind me again, how would negative w compare to positive w? Like if you had positive w, what would you do to turn it into negative w? Visually, just the opposite direction, just flip it around. Okay, it's like spin it around 180 degrees. So when you want to subtract two vectors, just take the opposite of the second one and add it. It's basically just doing something like this. If you don't understand how to do 2 minus 4, but you know how to add, well then just think of it as 2 plus negative 4. take the opposite of the second one and add. And that's really subtraction. Okay, so let's try an example here. Anyone have the directions that anyone that wanted to copy them? All right, so let's look at v minus w. So how am I going to think of v minus w? I don't want to think of it as having subtraction. I want to think of it a different way. Yeah. Yeah, let's think of it as v plus negative w. Again, just all my letters are bold when I'm talking about vectors. I'm not going to keep tracing over them 100 times. All right, so in order to do v plus negative w, Joe, do I have v?
Yes.
Yes, I do. Do I have negative w?
No, you do not.
No, I need to find it. So to get negative w, what did we say to? What did we say we have to do?
Change the direction.
Yeah, just change the direction. How about the length? Should I change that?
No, you keep the length.
Nope. So if I flip it horizontally and vertically, it's basically like rotating at 180. I just don't have a way to rotate 180 perfectly, but I can do that. So there's negative w. So now take v plus negative w and now connect them, and that's the answer for v minus w. Beginning of v to the end of negative w. And there's your answer. Any question on that? So that's how you do subtraction. Just take the second one, flip it around, and add it. All right, so we've added, back here, a vector to a vector. Vector plus vector. We just did vector minus vector. This is going to be a little different. This isn't going to be vector times vector. I'm not going to do that until Wednesday. That's a little different. We're going to do number times vector, like this. Take the vector v and put like a 3 in front. Does anyone have a guess before I explain it what that would do to it? It would do something to the vector v. Yeah?
I would change the length and make it 3 times as long.
Yeah, that particular one would triple the length of the vector. So scalar product is when you multiply a number by a vector. Not a vector times a vector. Number times vector. Now there's 3 things that could happen. Joe just named one of them. The vector could get longer. In the case of 3v, it gets 3 times as long. What else could happen to a vector when you scale it, besides getting longer?
Get shorter.
It could get shorter. That's the second thing that could happen. What about the third thing? I mean, it could stay the same if you multiply by a 1. We won't count that. So it gets longer, it gets shorter. Or what else could the number in front be?
0.
All right, if you multiply it by 0, then you basically wiped out your vector completely, and now you have the 0 vector. So you could do that. But it could be negative, and what would happen if you did that? What would that negative cause the vector to do? It would flip it. So the 3 things that can happen when you scale is you can shorten, you can lengthen, or you can flip the direction of a vector. But that's it. Shorten, lengthen, or reverse the direction. Okay, so let's try each of these. So we have 2v, again the v is bold, and 1/2 v. Well, if you think of 2v, like I want to find exactly 2v. I don't want to estimate it. How could you get 2v exactly? Like if you had graph paper, you could do it, perfect. But even without graph paper, I can do this. Yeah.
Couldn't you, using the smartboard, couldn't you make 2 of those and put them side to side?
Yeah. Just think of it as this. 2v is v plus v. That's 2 of them. Like x plus x is 2x. So, like Joe just said, take that, make a copy, make another copy, and there you go. There's your answer. But now just draw it out.
We don't do that.
That's 2v. And now you can't see it, so just move it off so you can actually see it. So it's a vector twice as long as the original, points in the same direction. What would that mean if this represented an object traveling? What's happening to the object now compared to before?
Twice as fast.
It's going twice as fast, but it's still going exactly the same way. Now 1/2 v, I don't really have a way to do that one like exact unless I get a ruler. So I'm just going to kind of estimate.
Oh, that's not half.
That's not half? You don't think so? I think it's pretty close. But yeah, if I had a ruler, you could make it better. Okay, so that's a 1/2 v. Again, both of those same direction, faster and slower. What if that was a force? What's the difference between, say, the original force and 1/2 v? Half as strong. So if I was pushing on something, I'm still pushing the same way, but I'm not pushing as hard. All right. Let's do v and negative v. Corey, what's going to happen here? V to negative v.
Change the direction.
It's going to change direction. Anything else?
Kind of short.
For which one? The first one or the second one is going to shorten? Not sure. Anyone have a thought which one of those is going to shorten? One of them's not. One of them's going to stay the same. Yeah.
The 1/3.
The 1/3, yeah, that's going to do 2 things. The 1/3 shortens it, the negative flips it. The first one, just a negative. It's a -1. So all it does is flip it. Now you could also see it like this. That's the same thing. All right, so for that one I can do perfect just by flipping horizontal and then flipping vertical. It's a theorem from geometry. If you do 2 reflections like that, it ends up being a 180-degree rotation. So that one I can do. Now the next one, I'm supposed to flip it, which I've already done, but I'm supposed to make it 1/3 as long. So unless I have a ruler for that one, I'll just estimate it. Is that 1/3 or?
It's more like a quarter.
That's more like a quarter. Yeah, it might be a little short. But that's the idea. Okay. Any questions on that one? So again, not too bad. Okay, so this is just kind of combining both things that we learned. Now we want to do addition, and we want to do a scalar product in the same problem. All right, so Eric, to do 2v plus 3w, what would I want to do first?
Like copy the V.
Yep.
And put one next to it.
All right, so let's copy it, put it next to it. So I'm just going to move that there. Okay, got it. So there's 2v, and now what do I need to do?
And then make 3W.
Okay. I need one more. All right, got it.
And then,
Wait, would those have to be connected?
yeah, like connect the 3Ws.
Yep. So put them all just like that. Again, think of it as a one-way street. All the traffic should be flowing the same way, or like a pipe, right? It's all going down. It's all going one direction. If If you have arrows meeting at each other, something's not right. So now, what's the last thing I have to do? Yep.
Like draw an arrow over all of them.
Which way?
Going the same way that they're all facing.
Right.
To the right.
Yep. The arrow should point
Oh yeah.
from the
Yeah.
start
Like
right to the
to the
finish.
end.
Just like that. So that's your answer. So notice what starts to happen is the arrow, it starts to get really big. So that's one downside of drawing it, is that you can go off the graph paper. All right, so that's a special symbol that you might see. It's like double bars around the V, or around whatever the vector is. That symbol means magnitude. So if you see this question in the homework and they say find the following, and they write this, they want you to say how long is the vector. Now, the vectors that we've been drawing so far, I haven't drawn them on any graph paper, so you can't really find the length of any of these. If it's on a piece of graph paper, you could. Anyone have an idea, like, if I throw in a piece of graph, like how you would find the length of that? Well, we'll get to it. We'll talk more about it, but a little bit. So magnitude is a length. It's always a positive number. So you'd never want to say the magnitude of this vector is -5. And if you said, well, wait, the vector is going down, shouldn't down be negative? No. The direction the arrow points takes care of the negative. If you measure the length, even if you measure down, measuring down is still a positive number if you have a tape measure. It's not going to say negative something. Okay, so magnitude is always positive. So keeping that in mind, what would be the difference between those two things? The magnitude of x and the magnitude of -x.
Nothing. Wouldn't they both be positive?
Yeah, nothing. There is no difference there. So those two things are exactly the same. So magnitude of x, magnitude of -x are the same. What's different is the direction that x and -x point. But if you're measuring them, that's like measuring the table from left to right and then measuring it from right to left. It's the same length, just a different direction you measure. Okay. Does anyone remember when we studied trig a while ago? We did it on a circle, and we did it on a special circle that had a radius of 1. Does anyone remember what that circle was called? It was a unit circle. Well, if you have a vector that's a length of 1, we call it a unit vector. Okay, so this section has, I know it's got a lot of vocabulary in it, but once we get through today, most of the other stuff tomorrow is calculations. So if you have a vector that's equal to 1 for its length, it's called a unit vector. All right, so if we really want to start doing more stuff with vectors, drawing them is going to take forever. All right, especially if you've got to add things that are decimals or they're really big. I mean, you're either going to have to measure things or get a bigger piece of graph paper, or it kind of gets to be a pain. So we've got to have a better way to represent vectors than drawing them all the time. Now, I'm not saying drawing is a bad thing. I think drawing is good if you have a word problem. Because to me, when somebody writes out a problem, I need to see it visually and see what's happening. But just for basic calculations, let's see if we can come up with a better way. Now, there's really two other ways besides drawing that you can do vectors. The first notation we're going to learn, and this isn't even the one that's used most often, but it is one that's in our books, so we'll look at it quick. It's called an algebraic vector. And it looks something like that. It uses two angled brackets, and then an A, comma B. A and B would just be numbers inside there. It's very important when you write this that you don't use parentheses. What would happen, or what do you think I would, if I looked at something like this, and I saw that, what do you think I would be thinking? It's a what?
Graphing a point.
That's graphing a point. That's a coordinate, right? We're talking about vectors, so you're going to see something like this. But what do each of those numbers mean? Well, I kind of started to tell you. One of them has to do with horizontal. One of them has to do with vertical, right? From a certain starting point.
So is that like finding the slope of it for the vector? Like the answer?
Well, it's kind of like if this was your graph paper, and you had your something like this, and you had a point here, and you had a point here. It's basically how many over do you go and how many up do you go. So it's kind of like the slope, but you don't write it as a single fraction. You put them separate. So yeah, this would be like 1, 2, 3, 1. So this would be the vector 3, 1. If I did that. So yeah, it's kind of like rise and run. But what we call them with vectors is components. Okay. Every vector, unless one of the components is 0, every vector has a horizontal and a vertical component. Okay. Think about if I throw something to you, right? If I throw it straight at you and it doesn't go up or down at all, then that's just coming at you horizontally. But think of like somebody like in baseball when they throw something from the outfield. They usually don't throw the ball perfectly straight. They usually throw it up a little bit. Because if they throw it straight, it's going to hit the ground. But if they throw it, not like straight up, but if they just throw it up a little bit, it makes it so it can stay in the air a little longer. So when they throw it, there's two components to the ball. It's going forward, but it's also going up. So if that represented how somebody threw an object, that dotted line right there would represent the horizontal component. And that dotted line right there would represent the vertical. Horizontal, vertical. Those would be the two components that make up that vector. And notice what shape I made when I did that.
Triangle.
Yeah, I ended up making a right triangle. So now, if you wanted to know how long that arrow is, well, you could use the Pythagorean theorem, and that would tell you how fast they threw the object, as long as you know each one of these. But we'll look at that more tomorrow. So, from a starting point, A tells you how far left and right to go. So, right here, there's my starting point. A was a 3. 1, 2, 3 to the right. Positive is right, negative is left. B tells you how far up and down to go, okay, to get to the ending point. So in my example, B was 1. I went 3 right, and I went 1 up. If B is positive, you go up. If B is negative, you go down. All right, so let's draw another vector. Let's draw the vector 4, 3. Now, this notation tells me a couple things. It tells me from an initial point. It's the first sentence. From an initial point, how far left and right, how far up and down. But what doesn't that tell me? It doesn't tell me something. All that says is go 4 right and go 3 up.
What if V equals it?
What it what?
Like how that other one had like V equals. And then
Okay, so it doesn't give it a name. It doesn't, I mean, we could call it like vector x if you wanted to, you know, give it a name. So vector x is represented numerically as 4, 3. But what else does this 4, 3 not tell me? Yeah?
Where to start?
Doesn't tell me where to start. So I could start right here and say go 1, 2, 3, 4, up 3. That's a perfectly acceptable way to draw the vector 4, 3. I could also go here. 1, 2, 3, 4, 1, 2, 3. That's another way to draw it. Or over here. Those are all the vector 4, 3. But there is a place that we usually start. Okay? Where do you think the most common place is for the start point, the initial point?
0, 0.
The origin.
The origin. So where we usually start at is the origin. So if the vector does start at the origin, that's called a position vector. None of these that I drew are position vectors. But we're going to take one of them, and we're going to figure out what the position vector would be. Okay? It's basically like figuring out, if I dragged one of those arrows, so it started at the origin, where would the terminal point be? Where would it end? That's basically what you're figuring out. So let's look at the one that's in quadrant 1. That's the easiest one to look at. Okay, and let's make it bigger so we can see it. Okay, so just focus on what's in quadrant 1. What's the coordinate of this point? 3, 3. Yep. And what about the coordinate of that point?
7, 6.
How much?
7, 6.
7, 6. Let's see. 1, 2, 3, 4, 5, 6, 7, and then 1, 2, 3, 4, 5, 6. Yep. Now, we already know the answer. The answer is 4, 3. Does anyone see what I could do with the coordinates from the initial and the terminal point to somehow get this answer?
Subtract.
Subtract them, yeah. If you take 7 minus 6 in that order, terminal minus initial, that gives you 4. 6 minus 3 gives you 3. That's how you find a position vector, right? You just subtract your coordinates. But make sure you subtract them in the right order. All right, so to find a position vector, if the initial point is not at the origin, this is how you do it. Now, I'm letting P1 be the initial point and P2 be the terminal point. P1, they could be called anything. X and Y, you know, whatever the points are called. You have an initial and you have a terminal. Your initial point has an X and Y coordinate, so does your terminal. To find the position vector, we just did it. Subtract your X's, make sure you do terminal minus initial, and then subtract your Y's. Terminal minus initial. What do you think would happen if you did initial minus terminal? Something would still come out right, but then something else about the vector would come out wrong. Anyone have a guess what would come out? Like if you got, you know, you did your position vector, but you accidentally reversed the order you subtracted.
It would just be going the wrong way.
The vector would be going the wrong way. If you were supposed to get something like this, you would get something like that. You'd get the right length, but you'd get the wrong direction. So make sure you do terminal minus initial. All right, so let's finish up by finding the position vector for these 2 points. Now, they didn't explicitly say which one is initial and which one is terminal, but if you had to use common sense, P1, P2, which one do you think is the starting point?
P1.
P1. P2, the one that comes after it, that's the ending point. Right, so Kiara, what am I going to subtract in the first part? What minus what?
4 minus negative 1.
4, can you just say it again?
4 minus negative 1.
Yes, 4 minus negative 1. So we'll come back to that, but that's exactly what you got to do. And how about Dylan? What about the second part?
6 minus 2.
6 minus 2. So what's my final answer for the position vector? 5, 4. So what we're saying there is if you were to draw this vector and have it start at the origin, it would end at the point 5 units to the right and 4 units up. So 5, 4. And that's the notation. Make sure you use those angled brackets. Any questions on that? All right, so the homework, you got to pay special attention to the directions because they're asking you to do something in the book we haven't done yet. So 1, 8 through 22 even, just do exactly what the directions say. But on 26 to 32 even, just find the position vector. They're going to ask you something about this, what's called unit vector notation, which has i's and j's in it. We haven't done that yet.
Yeah.
So on 26 to 32, just find the position vector.